Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 1, Limits and Continuity, and today's topic is Section 1.8, Determining Limits Using the Squeeze Theorem. Enjoy today's notes. All right, for Section 1.8, the Squeeze Theorem, we're going to start with what the Squeeze Theorem says. Side note, this is sometimes referred to as the Sandwich Theorem or even the Pinching Theorem, but the formal name of this is again called the Squeeze Theorem. What this says is if I've got three functions, so the function we're talking about is the one that's in the middle for this expression, that's going to be f of x. And we're going to say that it's being surrounded by below by a function g of x, and from above by a function which we're going to call h of x. And so this expression here is saying that the outputs for these functions, that f of x is between g of x and h of x. It is being squeezed or sandwiched between these two functions where g is fully below it and sometimes equal to it, and h is fully above it and sometimes equal to it. And so what the squeeze theorem here says that if those that statement is true, if those things are less than or equal to each other, and if the limit as x approaches some value a, some arbitrary value a of g of x, is equal to an output limit L, and the limit as x approaches a of h of x is also equal to L, then our conclusion, the limit as x approaches a of f of x is going to also be equal to L. So this is our first example of sort of a conditional statement, right? A conditional statement is sort of like an if and then. All of this needs to be true. If all of this stuff is true, then this is going to be true. And so we have to, if we're going to use the squeeze theorem, we're going to have to check that those statements are true for the if part before we can get to the then part. All right, let's see what this looks like in practice. The limit as x approaches 0 of x squared times cosine of 1 over x squared. Now, there is no nice algebraic technique that I can use in order to solve this. In fact, if we do our usual direct substitution, we would get 0 squared times cosine of 1 over 0. We would get this like weird undefined because we're dividing by 0. So that is no good. We cannot divide by 0. And so we don't get an answer if we do it that way. And so how do we find this? Well, even if we think back to those special trig rules that we have memorized regarding sine and cosine, none of them really work for this. We can't really get it in a way that we can use those. And so we're going to bring in this squeeze theorem. And in order to do this particular problem, I'm going to bring in some knowledge about how this function actually looks. We know that cosine, if we remember from either geometry or algebra 2, is a periodic function that sort of oscillates back and forth forever. If we're thinking about just cosine of x. And it does this in both directions, this oscillating motion. And one of the things that makes cosine what it is it goes up to a height of y equals 1, and it goes down to a height of y equals -1. And if you want to investigate this more, you're welcome to type that in your graphing calculator and check that out. But cosine goes up to 1 and goes down to -1. That is the range for cosine. So I'm going to use that to our advantage here, having a little bit of knowledge about what cosine is, to say here that I know that just this cosine part, cosine of anything, in this case 1 over x squared, has to be between -1 and 1. Has to be between it, because if we have a cosine function, the outputs can only be between those two values. So if I've got this 1 over x squared inside of the cosine, still can only give me outputs between 1 and -1. But we'll notice that that's not exactly what this limit says. It needs an x squared. So what I'm going to do is I'm going to say, okay, well, let's take this inequality that we've got, and I'm going to multiply by x squared in each part of the inequality. If we're going to keep that inequality balanced, we need to multiply in each of those three parts. If we do that, this is now going to become -x squared is less than or equal to x squared times cosine of 1 over x squared, which is less than or equal to 1 times x squared, which is x squared. If this statement is true, so now we've sort of got, if we're looking at our if part, this is our if part. So now we need to get to the limit piece. What are the limits of each of these things? Well, in this case, if I were to think about the limits of each of these things, the limit as x approaches 0, because that's what they asked us for, x approaches 0, of negative x squared should be less than or equal to the limit as x approaches 0 of x squared cosine of 1 over x squared, which should be less than or equal to the limit as x approaches 0 of positive x squared. All right, so what are these? Well, conveniently for us, the ones on the outside are very easy with direct substitution. We can plug those in. The limit as x approaches 0 of negative x squared is just going to be 0. And the limit as x approaches 0 of positive x squared is also 0. So what does that tell me? Well, this limit that I had in the middle, the limit as x approaches 0 of x squared times cosine of 1 over x squared, has to be between 0 and 0. We have successfully squeezed those outside parts together, which means if it's less than or equal to 0 and greater than or equal to 0, the only value that it can actually equal is 0. And so in conclusion, by the squeeze theorem, we know that the limit as x approaches 0 of x squared times cosine of 1 over x squared has to equal 0. That is the conclusion. That's the then part for our squeeze theorem. Nice. Moving on to number 2, let g and h be the functions defined by g of x is equal to negative x squared plus 2x minus 3, and h of x is equal to 2x plus 1. If f is a function that satisfies g of x is less than or equal to f of x, which is less than or equal to h of x, that's giving us part of the squeeze theorem, then what is the limit as x approaches 2 of f of x? Well, let's write out what we know. They said that g of x is less than or equal to f of x, which is less than or equal to h of x, which again looks very similar to our squeeze theorem. Let's substitute the equations that we know. We've got negative x squared plus 2x minus 3, and that's going to be less than or equal to whatever f of x is, which they didn't tell us, which is less than or equal to h of x, which is 2x plus 1. All right, well, that's a true statement they gave us. We're going to throw the limits in there for each of these. So the limit as x approaches 2 of that negative x squared plus 2x minus 3 has to be less than or equal to the limit as x approaches 2 of whatever f of x is, which is less than or equal to the limit as x approaches 2 of 2x plus 1. Okay, we added those limit statements. Now evaluate these ones on the outside. What are these going to give us? Well, if we substitute these in using direct substitution, we've got negative 2 squared, so that's a negative 4, plus 4 minus 3. And then over here I've got a 2 times 2 plus 1. So on the left that becomes a negative 3. On the right this looks like a 5. So I've got a less than or equal to the limit as x approaches 2 of f of x. Notice here that the values that we have are not the same. And if we go back to our original definition of what this is, we notice that those limits would have to be the same if we're going to be able to get to a conclusion. So because of that, the squeeze theorem does not actually apply to this problem. And so we found out that it actually cannot be determined. So the limit cannot be determined using the squeeze theorem. The only way that would be the case is if these values were the same, and this was not in this case. And so we don't know. We don't know using the squeeze theorem. That's not enough in order to do it. Okay. Let's continue. I'm going to erase. Oh, maybe will I erase? No, let's not. For number 3. So let g and h be the functions defined by this g of x and h of x. And they're saying g of x is less than or equal to f of x, which is less than or equal to h of x for -1 to 5. X is between -1 and 5. What is the limit as x approaches 0 of f of x? So in this case, we've got cosine of pi over 2x plus 2 is less than or equal to whatever f of x is, which is less than or equal to x squared plus 3. Again, we're going to want to, since they gave that to us, that's half of the if part for the squeeze theorem, we're going to want to essentially find the limit as x approaches 0 for each of these three parts. So each of those three parts, we want the limit as x approaches 0. All right, so if we want to evaluate this and we substitute the 0 in for our x, we end up with cosine of 0, which is simply 1. So 1 plus 2 is going to give us 3. That's going to be less than or equal to whatever the limit as x approaches 0 of f of x is. And if we substitute our 0 in for our x over here as well, we get 0 plus 3, which is 3. Notice, hey, these two values are equal to each other. And so that means that the limit has been successfully squeezed between these two functions, and we can conclude that the limit as x approaches 0 of f of x has to equal 3. And that's going to be our final answer for problem number 3 using the squeeze theorem. All right, that's number 3. To the last set of problems for this. Let f, g, and h be the functions defined by f of x, g of x, and h of x listed there for x is not equal to 0. All of the following inequalities are true for x is not equal to 0. State whether each inequality can be used with the squeeze theorem. So what are they asking us to do? State whether each inequality can be used with the squeeze theorem to find the limit. So they're not actually asking us to find out what the limit is necessarily. They just want to know, can we actually do it? And they're asking us to find the limit of the function as x approaches 0. Well, in this case, if we are thinking about the limit as x approaches 0 for this, the -1/2 it just is what it is. It's not changing. So this is the limit as x approaches 0 of f of x. And that should be less than or equal to, if we substitute 0 in for this x squared plus 1/2, the 0 squared is 0, and we're left with 1/2. And if I'm looking at my squeeze theorem, hey, I got a -1/2 and I got a +1/2. Those are not the same, so no, cannot use squeeze theorem. All right, that's number 4. Number 5, if again we're doing the limit as x approaches 0, if we plug in 0 for that -x cubed, we get 0 cubed, or -0 cubed, which is still 0. So that's going to be less than or equal to the limit as x approaches 0 of g of x, which is less than or equal to 0 cubed, which is 0. Hey, in this case we notice that both of these are the same. So yes, I'm going to put squeeze theorem applies. And in fact, we actually know that the limit as x approaches 0 of g of x has to equal 0 because those were both what it equaled on the outside. Last one, limit as x approaches 0 of 1 minus x squared. If we do that, that's going to be 1 minus 0, which is 1. So that's less than or equal to the limit as x approaches 0 of whatever h of x is. And then if we substitute 0 in for x squared plus 1, we get 0 plus 1, which is 1. And again, since both of these are the same, squeeze theorem applies. So yes, the squeeze theorem applies. And we know that the limit as x approaches 0 of h of x is equal to 1. That's it for today's notes. We've got some practice problems for you to try. Please do those and check your answers. Bring your questions to class. Let's make sure that we're using our class time and office hours to answer any questions that you've got. Have a great day.